Okay, so let's first figure out what is the gravitational potential energy. So let's say, let me just call it G. The gravitational potential energy is equal to, actually, what is it? Can somebody tell me how do you figure out the gravitational potential energy as a function of U of X?
Maybe rho GU.
Yeah, it's a rho. Yeah, right. That's well, if you say F is equal to rho X times G, that's right. So basically it's rho GU. Yes. The gravitational potential energy. This is basically if you say rho is the mass per unit length, then it's actually rho GU. Yeah, it's going to be integral from let's say this is 0, this is 1, from 0 to 1 of rho of X G times U of X dx, right? So that's how much gravitational potential energy you have. It's actually linear with respect to the deformation. How about the elastic potential energy? Let me just call it E. How would you describe E?
You would need to know the properties of the rope, right?
Yes, I need the property of the rope. So let's say the rope has an elastic coefficient of K. All right. How would you, so let's say it's a linear elastic rope whose the tension on the rope would be proportional to how much it lengthens. Well, this is actually a little bit tricky. So let me actually derive this for you. So let's say I have a rope that is initially flat, and then I deform it so that it actually slants down, right? Just like a section of the rope over here. Okay, initially it's flat, and now it's like that. So how much has it lengthened? So let's say if this is dx, and this is dx, and this section would be du, right? This is how much the rope has went down. U is how much the rope has went down, and du is the difference between u on this point and this point. So the rope has lengthened for du square plus dx square root minus dx, right? So that's the lengthening of this section of the rope. And here, let's actually look at the linear case. And the linear case means du is much smaller than dx. So basically, the slope of the string is it's small. Let's say if we discuss in this case, and if that is the case, we can do basically a Taylor series analysis in the following way. We can pull dx out of this equation, right? This is equal to something times dx, and that something is square root of du dx square plus 1 minus 1, right? Agreed? I'm just pulling dx out of everything. Okay, and if du dx is much smaller than 1, you can actually do a Taylor series analysis to the function, to this function of 1 plus, let's see, 1 plus epsilon square root, right? You can do Taylor series and figure out, okay, what is this function if you do Taylor series analysis. First of all, when epsilon is equal to 0 is equal to 1, and when epsilon, oops, and when epsilon is come on, Okay, when epsilon is small, you take derivative of this function with respect to epsilon. The square root gives you a half, and the square gives you a 2, so they cancel, and you end up with plus epsilon, plus O epsilon squared, right? So this is what you do with Taylor series. And then if you ignore the epsilon squared term, if du dx is small, what you get is du dx times dx. Right? Let's see. Oh no, actually, if it's x square. Oh, sorry. You do Taylor series analysis, and the first order first order derivative is actually 0. The second order derivative is actually going to be, let's see, the second order. Okay, sorry. If you take the derivative of this guy, you get square root of 1 plus epsilon square 2 epsilon, right? So this is the first order derivative. When epsilon is 0, it's equal to 0, and you have to take the second order derivative to get a 1. So this is actually 0, epsilon squared, right? So essentially, what you get is du dx squared times dx. That's how much the string has lengthened. Okay,